Okay, we are going to talk about the fundamental theorem of calculus today. Must we? Yeah, we must.
Make up a card?
We must. This is the very mathematically looking statement of the fundamental theorem of calculus. Would you like to know what it says in English?
Can I ask a question?
Sure.
What are we going to use this for?
You're going to use it. You're going to apply it. To finding accumulated area between two graphs, which will work out to be a useful thing. Okay. Now, this first part here actually says that if you have an integral and it has actual limits to its integration, it is what we call a definite integral, that you take the antiderivative and you plug in the value of b, and then you plug in the value of a, and you subtract the two answers. That's really all it says. Okay? Or you put it in your calculator. That won't get you anywhere, though. Okay, so for example, here we have the integral from 1 to 3 of 3x squared dx. And the value of, and I think we've actually even already talked about this. We've already talked about this, so this is just, since you took the test, kind of reminding you. The integral of 3x squared dx is x cubed plus some constant. Okay, so if you have x cubed and you plug in 3, you get 27. And if you plug in 1, you get 1. And on both of those, if you have c minus c, c blows up and goes away. So the constant makes no difference, and the final answer is just simply 26. Remember?
Where did you get negative 1 at?
You're subtracting the two.
Okay.
That's what the rule says too. You subtract the lower one from the higher.
All right, I got you.
Okay?
So what if
You
we
just
find
take
the-
this shit, put this shit in that. I'm going to do this shit. Oh.
I do not know what we're going to do with you, Brandon. Okay, now it can get more complicated than that, but that basically is what it is.
You take these numbers,
These are all the properties, and all this basically says is that if there's not a difference between A and B, the two limits of integration, then you don't have an area.
me and him are both confused on why dx is there. Is that dx just telling you that
dx is telling you that what was in front of it was the derivative.
What page are we on?
11.
So it's pointless stuff, essentially. I said stuff this time, too.
It's just a notation thing. Just like you had the delta y over delta x for the how you find slope, or d over dx because derivatives are.
In the problem. We didn't have to throw delta y over delta x in the problem.
No, you avoided that by saying y prime or f prime of x, but that's the same thing as dy over dx.
So we go back to the example.
There's like 6 ways to say
Yeah, but it's not worked out.
it's a real square. Essentially, dx is just pointless.
Okay, this is the integral. This is this actually is dy dx. This is the derivative with respect to x. That's what that's saying.
Yes, I understand.
Okay.
That, but it's not gonna whenever we see it, we just ignore it pretty much.
You can ignore it, but if you forget to put it in, if it were to ask you that on my math lab, then it's going to count it wrong because it's part of. But it isn't going to ask you, as far as I know, any of the ones you've got.
It's pointless for us to know at this second. For the problem, to work out the problem.
Right. You don't need to know it for this one because all you have to know is that this is the derivative of some function.
We're just we keep looking at x and we're thinking, well, we need to plug something in.
Yeah, but you don't.
That's why I said it's pointless, really. It's like,
Just ignore it. It's just basically the notation of an integral.
oh.
Oh. Yeah, this quantity, the integral of 3x squared dx, is x cubed, because 3x squared is the derivative of x cubed.
So does the C matter? Is that where the one's coming from?
No, the c is a constant, and
It's going to be constant forever.
the c is just the constant that's hanging out on the end of the problem. It might be 0, it might be negative 12, it might be 2 billion, but it's just a number.
It just tells you just to add the one is just
Okay? So when you do the integral, you find what 3x squared is the derivative of. It's the derivative of x cubed plus some number.
You always just put plus
Yeah, plus c. You don't know what c is without, you have to have more information to find out the value of c. Okay?
do that.
So when you do, well actually if we were going to 16 we would, but we're not.
Is this the last chapter?
Hmm?
Is this the last
This is
chapter?
it.
I like it.
This is it. We finished 15 and we are done. Right. You take the 3 and plug it into x cubed, and you take the 1 and plug it into x cubed, and then you subtract. That's it. Okay?
Okay.
And that's the basic method for all of these.
Okay.
That's the basic method for all of them. Because if you have 3 squared plus c minus 1 squared plus c, then it's c minus c, and they cancel. Okay, anybody else questions? Because this is the most basic place to start. So, taking the integral is not complicated. You have to understand the steps. Okay? Poor girl. Okay. All these are properties of integrals. They correspond to the properties that you had of doing derivatives. Okay? It actually also corresponds to the properties of doing integrals from the first section. The only difference is now we got an A and a B hanging off the integral sign. Okay? So here's the second example. The way that we use the rule is you take the integral of the first term minus the integral of the second term, added to the integral of the third term, and then you plug in your constants, your limits. So the integral of x cubed, add 1 to the power, and then divide by the power. The 2 just parks itself out in front because it doesn't do anything but ride along. Okay? So it's 2 times x to the 4th over 4. And this says when we get done, we're going to plug in 3 into that expression, and plug in 5 into that expression, and subtract.
Why did we divide all four?
Because that's how, originally that x cubed had a coefficient in front of it, and its power was 1 higher. So when we integrate, we're going backwards from derivatives. So instead of subtracting 1 from the power and then multiplying by it, or bring the power, I'm sorry, let me start over. Instead of taking the power and bringing it down front and multiplying by it and then subtracting 1 from the power, we're going backwards. So we add 1 back to the power, and then we take that thing that we had dropped down in front and we divide by it. You're undoing what you did when you did the derivative. Okay?
So, divide by 4, basically divide by
Whatever the new power is.
Okay.
Okay? And we're going to do the same thing here. The 3 there is just along for the ride. This is x to the first, so raise that power to x squared, and then take that 2 and put it down underneath, and divide by it.
So really, you just take your
Get rid
well,
of
no,
the power.
I'm thinking numbers. You just take your numbers out of the problem for a second, and you just worry about your powers.
Powers.
Right.
Yes. None of the derivative part of this is new. The only thing that's new is plugging in the 2 numbers at the end and subtracting. Okay? So when we have the integral of 4, for example, well, there used to be an x there. Okay? So we put the x back in and divide by that first power of the x, which doesn't change anything. But I mean, it's following the rule for the power rule, okay? So then 2 goes into 4 2 times, so this out front is 1/2. 1/2 x to the 4th. 3 over 2 is 3/2, and the 4 is still sitting out here. And all you do is plug in 5 to the 4th, and 3 to the 4th, and subtract. And then 5 squared, and 3 squared, and subtract. And then 5 and 3, and then subtract. Okay? So 5 to the 4th is 625. 3 to the 4th is 81. 5 squared is 25. 3 squared is 9. And then you've got 5 and 3. Subtract these two numbers, subtract those two numbers, subtract those two numbers, and then multiply them by the number in front of the parentheses, and you should get 256.
So what is
256 is the area that is underneath the graph of 2x cubed minus 3x plus 4 if you start at 3 and go to 5. That's the actual area between the x-axis and that curve. Okay? The only way the answer would be a negative is if the curve is actually under the x-axis, and then it regards that area as being negative. And we're going to see a problem where you actually have to break up your integral at the point that your function crosses the x-axis, so that you get a negative area and a positive area, and that it adds the negative to the positive and actually takes away some of the total area. So what we want to find here is find the area of the region between the x-axis and the graph of x squared minus 3x, and we want to start that area at x equals 1, and we want to end it at x equals 3. And I actually have a graph of that. This is what it looks like. And in this case, this area is actually going to be considered negative because it's below the x-axis, not above it. Okay? So when we do this problem, we're going to do the integral of x squared, which is going to be x cubed over 3. And then we're going to do the integral of 3x, which is going to be 3 times x squared over 2. And then we're going to plug in the limits, and we're going to get the area. So it looks like this. It has the absolute value around it because, well, actually area is not negative. Yeah, the answer actually, the result has to be positive. Unless you've got a negative area added to a positive area, then you combine them before you do anything. Because otherwise you wind up with too much area. Okay? Now there is a meaning to that being negative. Like if that curve was a profit curve and you're looking at accumulated profit over a period of time, well, that's accumulated loss, not profit. Okay? And this is the one I was mentioning to you, the area between the x-axis and the graph of f of x equals x squared minus 4. You've got part of that area is actually negative and part of it is positive. So when you combine these two, you're finding the difference between those two areas as far as being the total area. So the way that we work that problem is you do the integral from 0 to 2 of x squared minus 4. The integral of x squared is 1/3 x cubed, or x cubed over 3. The integral of 4 is 4x over 1, or just 4x. And you're going to plug in to this formula, you're going to plug in 0 and 2 for the part that's below the x-axis, and then 2 and 4 for the part that's above the x-axis, because the areas are going to be different. Why? Okay.
You don't even have to work it out.
Brandon is spoiling all the secrets.
No, I'm not his.
You actually can check your answers by putting it in the calculator.
Why can't we just do it that way?
Well, on problems where it's possible to do that, we're going to. We're going to.
Figure out which side's bigger, by how much. You just put them both in there and then you figure it out.
Okay.
You graph and look at them both.
And actually doing this one on the calculator is really a good idea because it lets you check the fact that the area is going to be 16. Because this area actually is negative. But they take the absolute value of it and add it to this area and you get 16.
I got it negative.
You just gotta remember to make a positive.
Yeah.
Area's never gonna be negative.
If it says it's negative area, it's just below the x-axis.
Answer and go to math, or actually,
So example 3, you got 10 over 3.
go back to the example.
Yes.
No, example 3. Not 4.
Yeah, one more.
Okay, good. Yeah.
Okay?
When you're dealing with area, you're never gonna have negative area.
Right.
Think about it.
You can't have
It's not
negative
about the
area.
area of a box and it's negative. You obviously don't have a box.
One thing, black hole.
Yeah.
It could be in a black hole.
We're not astrophysics and scientists, whatever they are.
Okay. Something you may not have realized is that you can put in x squared. No, I'm going to show you something else. So there's the function that we're going to integrate. I'm going to do exactly what I know you did. You're going to go down to number 9. Tell it that you want the integral of y1, but I think the arguments may.
You showed us this a couple classes.
Yeah, I did.
Yeah.
So remind me which argument comes first, Kurt.
84 plus.
Is it the x and then the variable
You can do it with
expression?
But
Okay. So vars, y vars function y1, then the variable, which is x, and then the two limits, which in this case I want to be 1 and 3.
do you put the higher number first?
Put the lower number first. Okay? And I'm going to go up here and set my window. Let's just go from 0 to 5. And then I really don't want to see that particular, well, we'll go ahead and look at that function anyway. We're going to see the graph of the derivative is what we're going to see.
This is my computer.
Trio? That, what is that?
Yeah, but bigger now, I can't up on the inside, I like it.
Okay. Here's what I've got on the calculator, and if it ever gets done integrating, I will show you in a second. Because I forgot to set my y-axis, I just set the x. It has to think a long time about integration. Should stop? Okay. Well, it finally fixed itself anyway, I think. So we need to go in the negative direction on y also. And I don't think we really necessarily need to go to 15, but I'll leave that. Okay. There's the function that we're integrating. Now what it's doing here, notice there's a line coming out that way. But that line very slowly appearing is actually the value of the integral, which is this area under the x-axis. Okay? Notice it's a horizontal line, which means it's a y equals something. Well, y equals 10/3. And it happens to be negative, so it's below the y-axis. But it's telling you this area in here is 10/3. Okay? And the only reason it shows it to be negative is because it comes up under the x-axis instead of over the top of it. So it thinks it flipped it over, but it really didn't. Okay? I want the 10/3 because area is not negative. Yeah, you always want your area to be positive. Okay, and we've looked at this one before, but just where am I going to use this? Well, one of the things, folks. If you have the derivative of the yearly rate of consumption, which would be a derivative because it's a rate of change of natural gas, and it follows this function, which they can do modeling and get the function. So, I mean, this is a realistic function. And this is measured in trillions of cubic feet. Time is in years, and t equals 0 corresponds to 2,000. Then we wanted to know what the total amount used in the 10-year period from 2000 to 2010 is. We would integrate this function from 0 to 10. So when we do that, the integral of t is t squared over 2. The integral of e raised to a power is, as it always was, e raised to that power, and then you wind up dividing by the derivative of that power. Okay? And so we have, if you plug in 0, well, you get 0. Okay? If you plug in 0, you're going to get 0. That's all there is to it. T squared over 2 is 0, and e to the 0 power is just going to be that 100. Okay? So when you plug in the numbers, that amount at the end turns out to be 60.5. So that tells you that that city, that one single city, used 60.5 trillion cubic feet of natural gas between 2000 and 2010. That's a lot of gas. That was a great great consumption of natural resources, and like you said, a lot of it's going to get spewed back out into the air as pollution. So there's that too. But that is a lot of gas. So now we are ready to move to something new. The area between two curves. Not between the curve and the x-axis, but between two curves. It's on the Tegrity, and I think I put the whole PowerPoint up in D2L. Okay. You can also find the area between two curves, which can be a useful thing if you have two related quantities.
What page is it on?
14, I think. 13. Bottom of 13. So basically what this says, if you're looking for the area between two different functions, you find the area of the first function with the limits and the area of the second function with the limits, and then subtract them. Okay? So basically what happens here, if this is f of x and this is g of x, and you want to know what the area is between f of x and g of x, then you take the pink area off of the blue area and you wind up with just this. That's why it's a subtraction process. So the first one is kind of an abstract example. It says find the area bounded by these two functions. One of them is a linear function. The other one is a quadratic function, a parabola, and we want to find the area between the line and the parabola for x equals -1 to x equals +2. So g of x is the linear function, 2x plus 4. The derivative, it is the derivative of a function, so we're going to take the integral of 2x plus 4, which means that this is going to be x squared over 2 times 2, which leaves you with just x squared. And this is going to be 4x. And then negative x squared is going to become negative x to the third over 3. You want to subtract, it's usually top minus bottom. So whatever function is over the other one. You have to really look at a graph to determine which is which.
Oh,
Okay? So then the integral of f of x, which is the negative x squared plus 1, is, well, all right, they actually went ahead and changed this and said that's plus x squared. And then minus 1. So the integral of x squared is going to be x to the third over 3, and I'm not sure what they did with that.
So does it matter which order the functions come in at all?
You want the top one to come first. I'm sorry, actually, I don't know that it makes any difference. I don't know that because all it's going to do is switch the signs.
And you know the absolute value.
Yeah, and you're doing the absolute value, it doesn't matter. So, no, I don't think it makes any difference.
That's how I used to do my math problems. Like, anytime I knew it was going to be, I just flipped them around and I
Yeah.
did it.
Because if you took f of x minus g of x, all it's going to do is change some signs.
So the answer you get at the end is basically what you started with at 15.
Okay, here's g of... The reason that they're doing it the order they are is because g of x basically is the upper function. It's above the parabola.
I see what you're, I see.
Okay? And then f of x is actually below the line in all cases, so that's why they chose the order they did. But,
So if you know what the graph looks, really logically you're going to want to put the other one before the
yeah, and it just makes sense because it's going to have the more area under that graph. So you wind up, since all they did was they plugged in these two functions, they cleaned it up, and then they took the integral of it. So, here's the actual formula. X to the third over 3, it's all going in order now. X to the third over 3 plus x squared plus 3x. Plug in your 2, you get this expression. Plug in your -1, you get this one. It turns out to be 15, or you can put in f of x, which was back to the original problem. F of x is negative x squared plus 1 and g of x is 2x plus 4. I'm not going to have it actually graph the integral just yet, so I'm going to turn that one off because I have to change what it's going to look like anyway. So if we're looking from -4 to say about 4, yeah, that should do it. So we're trying to find the area from here to about here. Actually, I'm going to change this to the limits of integration, so it's from -1 to 2. So what we're finding is the area here. The area between those two functions. I think it's in D2L. If it's not, I'll put it up after class. Because I took the PowerPoint and made it into a PDF so that you could page through it faster. So if I go back here and I tell it I want to find the integral of not just y1, I want it to be y3 minus y1. And I want the limits to go from -1 to 2. And I can graph it, but it's just going to be a straight line once again. And it may not even show up on the window. No, I don't think it will because of the value of it. Yeah, it's not even going to be on that window. So it's still graphing away. But what is much more useful is to just go here. This is the part where you all that like calculator tricks might want to pay attention. Thank you. Since I put the integral in y2, vars, y vars, function, and my mouse is not wanting to move. It tells me what y2 is. It gives me the result of the integral. Okay? So that's how you find the area between two curves. Now, what's that good for? Well, I've got some more examples here, but we're not going to worry about them. I'm going to go to an example where you apply it. Company is considering a new manufacturing process in one of its plants. The new process provides substantial initial savings, with the savings declining with time according to the rate of savings function S prime of t is equal to 1 minus t squared. S prime of t is in thousands of dollars per year. At the same time that their savings is declining, the cost of operating the new process increases with time t. So they're going to save some money, but they're also going to have to spend some money. So the derivative of the cost function is t squared plus 14 over 3t. And that's also in thousands of dollars per year. It's important that the units on these two match, because it's going to be the units for your answer. So basically, this is what we're looking at. Now tell me about what's happening here. You have savings, which is following this. You have cost, which is following this. What do you suppose that blue area represents? It actually is it's S minus C. But what is S minus C? Savings minus cost, which is profit or revenue or accumulated revenue through the time. So for how many years will the company realize savings? And then what will be the net total savings during that period? Okay? Well, first of all, you need to know where those two graphs intersect. And they intersect where t squared plus 14 over 3t is equal to 100 minus t squared. And you can actually do this one pretty quickly because t squared and t squared are going to make this whole thing be a quadratic. It's going to wind up being 2t plus 14 over 3t minus 100 is equal to 0. And then solve and find where those roots are for that quadratic equation. Or, more simply, we can just go over here and graph it. Negative x squared plus 14 over 3 times x and then the function is 100 minus x squared. And I'm going to turn that function integral off there because it just makes the graph go really slowly. And we'll look on a window. Well, time's not going to be negative, so it probably just go to 0. And, you know, what happens over the first 10 years? And I'm going to do a zoom 0 on this, so we at least have a chance of seeing it. Yeah. I think I flipped something around. Yeah. Let me go back to the original functions here and put them in again. So it's not that one's not negative. X squared plus 14 over times x. Okay, that one's good now. The other one's 100 minus x squared. It says 100 on the graph, but this says 1. And 100 years doesn't make any sense. Doesn't make a bit of sense.
Don't you love these PowerPoints?
Well, when I know what I'm doing and I don't notice that they put something stupid in there, yeah. So this shouldn't be 100. That should be 1. I change it because it's a picture. Back to the problem. Let me fix it in the calculator. That's just supposed to be 1, not 100. And then try zoom again. I think we might get something closer to what the graph's supposed to look like. There we go. No.